Yeah. All right. So hello, everyone. Welcome to the 1W-MINDS seminar this week. We are very happy to have Professor Yi here today to give the seminar. He is a university research professor in the Department of Mathematics at the University of Kentucky. He has served as an editor for many journals, including the Qiang Journal of Matrix Analysis and Applications, Numerical Control and Optimization, and Electronic Transactions on Numerical Analysis. His research interests are varied and include numerical linear algebra analysis and machine learning algorithms and the analysis of those algorithms, which I think we'll be able to see some of today. And I'm looking forward to seeing what he's been working on recently. So I'll turn things over to you, Professor Yi.
Okay, thank you, Mark, for your introduction and for your invitations. It's a great pleasure and honor to join this distinguished seminar series. So I just mentioned to you, I'm actually new to the area of deep learning. So I'm going to talk about something called batch normalizations and the technique we used to improve that with preconditioning. So this is a joint work with my students, Susanna Lange and Kyle Helfrich. Okay, so here's the outline. I will start with a brief introduction to deep learning, and then I will describe the batch normalization in some details. And then I will talk about our work using batch normalization for preconditioning to accelerate the training. And so first three topics I will focus on the basic neural network called fully connected network. After that, I will talk about applications to the convolutional network. And then finally, I would end with some experiments and the concluding remarks. Okay. All right, so first some brief introduction to deep learning. So we're interested in the supervised learning. So in this task, we're given a label data set, xi, yi. So yi is labeled for xi. So what we want is to find the mapping from x to y. So what we do that by fitting a parametric family of function, was f of x theta, to the data. Okay. So to solve this problem, typically involves three steps. So first, we need to choose a parametric family of functions. Classical linear regression, use linear functions or things like that. So in deep learning, we used deep neural networks for f of x theta. Once we have a family of functions chosen, then we need to choose a loss function for the model output and the label. F of x theta is also called model or machines. Once we have the loss chosen, then we go to fit the data by finding the theta to minimize the mean loss. Okay, we also call empirical risk. So let's look at each of that in a little more details. So first, deep neural network. A neural network is just input-output relations defined by a compositions of L functions like this here. So each function there is a simple, basically affine transformation combined with a simple nonlinear function G. And G here is a simple nonlinear functions such as ReLU, but traditionally have logistic sigmoid, etc., have also been used. So this G is applied element-wise to this vector here. It's called activation functions. Okay. So this is typically incorporated as a neural network. So here HL, the intermediate variables, also called hidden variables. By the way, H0 is the input X. So from input X, it's a vector here. You can think of it as a bunch of neurons. And from X, you construct H1 through this simple linear function with G. And then from H1, you can construct H2 and so on to yield a output. Now, in this simple network, every neuron is connected to all the neurons in the previous layer. There is this weight matrix here is a dense matrix. So that's also called fully connected network. So, all right. So the second step is to choose a loss function, and that depends on the task you have. So for the model output, what I have, if the task is a regression problem, then you typically, meaning the label is a real vector. So typically we use the mean square error, basically just the two-norm of the error. By the way, the norm will always be the two-norm throughout this talk. And if it's a classification problem, then the label usually is so-called one-hot vector or just standard coordinate vectors. In that case, the output yi is usually scaled to be a probability distributions. So a probability vector, in that case, a suitable loss would be something called cross entropies. Now, with the loss chosen, then we go to optimize the models. So we find theta to minimize L. So for large-scale models, the gradient descent is basically the only methods that are practical. So for a gradient descent like this, the step size lambda is called learning rate. And then we need to compute the gradient of the loss functions. That can usually be computed very cheaply by something called backpropagation algorithms, which is really just chain rule, but it can be computed at about the same cost as the forward propagation, that is computed as theta. And another important aspect of the neural network training is that typically we use mini batch training. So typically the data set is very large, so you don't, it's not efficient to train, to use the mean loss over the entire data set. So typically we sample a subset of the data and then look at the loss over that subset called mini batch and do the gradients descent. So when you do a new iterations, you will sample a new data set and so on. Okay, so that's typically called mini batch stochastic gradient descent. Now, gradient descent is a very slow method, as you probably know. So to usually need to use some other, need to be combined with some acceleration technique. So here are a list of the methods that's often used in deep learning. So batch normalization here is one of them. So I'm going to talk about batch normalization in some more details now. So batch normalization is a way, as I said, to accelerate the training. So let's consider one of the hidden layers called else layer. So here the layer input is HL-1 and alpha is HL. Then during the mini batch training, we're given the input. I'm just going to label that input as n of n samples. Okay. So with x1, x2, xn, then we produce a corresponding n hidden variables, n features at HL-1. So I'm going to write that as h1, h2, hn. So the batch normalization observed that for the mini batch training, there's something called internal covariance shift. This during the training, this is happens when the statistics of a hidden variable changes during the training. So that is, if you look at the median variance of this mini batch of hidden variable here, when we train over a new mini batch with a new input, then the statistic, the median variance of this H might change, okay, due to the change of the input. Now, if that change, that creates some difficulty in training of WL, which was trained over a data set with certain median variance, when in the new training step, the mini batch changes, then the statistic change. So WL, the way we try to train, will have to adapt to that change of the mini-batch statistic. So this is called internal covariance shift. And they believe that slowed down for training. So that's one of the reasons for the covariance shift, but the training itself also causes the covariance shift. So when you train, you change the weight and bias, and because of for deep neural networks, a slight change at the early layers will create a large change for the later layer. So over one training step, you will also have covariance shift happens. All right, so a simple way to address this in the so-called batch normalization is to normalize the hidden variables HL-1 to have standard mean and variance. So the BN, here's what BN does. It replaces HL-1 by a BN operator here to I call B of HL-1. And this operator is this one here. What it does is take the HL-1 minus by mean and its variance over the mini batch. So that will normalize HL-1 to have 0 means and unit variance. Now, BN also recognized that the ideal input may not be the normalized variables. So they have another variable gamma and beta to rescale this input to have variance gamma and to shift the center to beta. Okay, so but with this transformation, then when you change the mini batch during the training, at least the mean variance of this variable going into the weight is not changed. I mean, other than the change in beta gamma. So this simple technique turns out to be very effective. It has produced faster convergence, accelerated convergence. It also allowed the training to use a larger learning rate, and it also found it's also found to have better generalizations. Okay. However, the BN method is not well understood. I mean, there are only limited analysis in trying to understand how this works. Okay, so there are a few things we know is that it's invariant to scaling of the weight and bias, and then it also we know that it improves the Lipschitzness of the loss. It is to improve the Lipschitz constant of the loss, and improve the bound of the Hessians. The full convergence analysis has only been done for some very special networks with like least square problems for 1 layer or 2 layer networks. Okay. So here's some challenge in the BN methods. So first of all, the network that we use for training depends on the mini batch. That is because we have this operator B inserted in the network architecture. So when the mini batch changes, when the input changes, the mini batch changes, then the whole network changes. So in other words, so in one iteration, I have a network, let's say trained. So when I go to do the next iterations, we need to use a new mini batch. Now, with a new mini batch, even if I don't do any training, that network has already been changed because of the mean and variance that's contained in the network is changed. Okay, so because of that, so when the network is changed, I mean it's trained, we use that to do inference. Then the inference network is quite different from the training network because for the inference network, of course, typically we just have one input. We want to find out the label for one input. We don't have a mini batch input. So the way the BN implement the inference network is that they just use some kind of average of the mu A and sigma A from the training iterations. So it seems to work well, but then there's a theoretical gap there in how these things works. Another difficulty of BN is that it doesn't work well with small mini batch size. So if you use a small mini batch size, BM may actually be worse than the plain network. Okay. Another issue might be because of the lack of theoretical understanding, so it's not straightforward in how to apply BN to other network architectures. So for example, when BN is applied to CNN, the mean and variance are computed in some particular way. So, but that's not, it's not clear why. Okay. And the same for RNNs, recurrent neural networks. Here I list a few alternatives that have been developed to address the small, some of the issues here. So batch renorm is one that try to reconcile the training and the inference network. And layer norm is to do the normalization instead of over mini batch. It does normalization over the neuron itself. So for example, for the hidden variables, instead of doing normalization over the several hidden variable over a mini batch input, is normalized over the neurons, that is entries of the vectors. And the group normalization is something similar, but for the CNNs and using over several channels. And there are also methods that try to combine these with BN to improve BN's performance with small mini batches. All right, so now I'm going to talk about our approach, preconditioning. So first I'm going to describe the standard precondition gradient descent. So let's look at the gradient descent, the standard one. So the standard result about convergence is that local convergence for the local minimizers, then the error is reduced by R, and epsilon here is just arbitrary small epsilons. So in a small neighborhood, we have this error is reduced by R the rate. The lambda min and lambda max here are the minimum and maximum eigenvalues of the Hessian matrix. So from this simple bounds, immediately we know that well, the learning rate alpha need to be less than 2 over the norm of the Hessian matrix. That's 2 over the lambda max. And also the optimal learning rate is kappa minus 1 over kappa plus 1, and kappa is the condition number in spectral norm in 2 norms of the Hessian matrix at the minimizer. So the rate of convergence depends on the Hessian condition number of the Hessians. So the preconditioning method is to try to use a linear transformation or change of variables to improve the condition number of the Hessian. So let's consider a change of variables theta is PZ. So the loss is just, this is the loss for a single input, just L theta LPZ. So if we do the gradient descent in Z, so that's a standard gradient descent, then what we have here is the gradient of L with respect to Z, and gradient theta times P. Now, if I multiply this equation by P from the left, then I got the theta K plus 1 and then theta K here. P times ZK becomes theta K. And then I have PP transpose gradient. So I have an equivalent iteration in terms of theta. Now, the only thing different here is the gradient in theta is multiplied by PP transpose. Okay. And that's the effect of the change of variables.
Now, so there's a question about the differentiability of the function and how much it makes sense to talk about the Hessian.
Oh, I will always assume it's twice differentiable. So although the neural network is with the say ReLU, depending on the activation function, the ReLU activation function is not twice differentiable, but it's almost everywhere twice differentiable. So usually it's not an issue. but for theoretical purpose, it's we always assume it's twice differentiable with Hessian, continuous Hessian.
Okay, thanks.
Okay, thank you. So the effect of this transformation on the convergence is that now the rate depends on the condition number of the Hessian with respect to Z. And that Hessian with respect to Z is this one. It's this guy here. It's multiplied by P from right and P transpose from the left. Okay. So a preconditioning method would be, well, I just choose P such that this matrix has better condition number. So if I have a better condition number, then we accelerate the convergence. Okay. All right. So that's just a general preconditioning method. It's used a lot in numerical linear algebra for solving linear systems. So now let's look at applying this to neural network. So for that, first I need to set up some notation to simplify things. So let's look at one layer, hidden layer here. And then let Wi be the ith row of the weight matrix there. I'm just going to consider one row and the one entry of bias. Okay, just consider one at a time. Then the corresponding ith entry of this affine transformation here can be it's just this the row ith row W times HL minus 1 plus BI. And this one I can make it look a little nicer by writing that in this homogeneous form. So here W is is stacking BI and WI together, and H had just add 1 to the top of H. Okay, so just write it in this nicer form here. Now remember, WI and BI are the parameters of the neural network, are the actual variable we want to optimize. Okay, so they are the variable here. So W hat is the variable here. So here's a theorem. It's a very, very simple theorem. Basically, just computer derivatives to find out the Hessians. Okay. Oops. All right. So if I write if I have a loss function, so loss function would be a function of W hat H hat through AIL. So I write it as a L of that variable. Now, when I train the loss over a mini batch of input and inputs. So let the H1, H2, Hn be the corresponding hidden variable at layer L minus 1 to denote by that. And I also add 1 to that vector called the Hj hat. Okay. Then in the training, we actually used mean loss, which is just 1/n of the sum of the loss over the n examples from the mini batch. Okay, so for this mean loss, then the gradient has this form here. So it's H hat transpose S H hat. What is H hat? H hat has this matrix here that has 2 block columns. So first it's just 1, 1, 1, 1. Usually I use the E for the vectors. And then the second block column is just transpose. You take each HI, take transpose, make it rows, put them together. Okay, so that's just a matrix of n rows of basically the mini batch of the hidden variables. And the S in the matrix in the middle is the diagonal matrix with second order derivatives. So you can see this form. I mean, as I said, this is very easy to prove, but the main contribution here is that to write it in the form that separate out the 2 different informations that affect the Hessian gradients. S here, of course, in the middle depends on the second order derivative of L, so that depends on the loss, etc., and network, etc. That part usually we don't try to improve because we simply don't have the information on that. I mean, to get information about that is much more expensive. But the other thing that determines this matrix is this H hat, and that depends on the mini batch. So one depends on L double prime, and the other one depends on the mini batch. And this mini batch could create a very bad conditioning, because if you look at this H1 here, if some of the entries of H1 have very different scale, let's say the first entry has scale 1, and the second entry has scale 10 to the -5. Then basically you look at the second column here is of order 1, and the second column 10 to the -5. In that case, H hat would be very, very bad, ill conditioned. Okay, so it's this one, the potential ill condition of H hat we try to address using preconditioning. So we do that by the transformation PZ as before, but now P is defined as product of these two matrices here. So U is a block upper triangular matrix, and with one the diagonal just negative mu A in the upper triangular part here, and mu A is the mean of the rows of the mean vectors. It's a vector mean of the row vectors of the H there. So it's just the mean of all the activation Hj. And sigma is just the variance. Okay. All right. So if I use this P as preconditioning, then with this transformation, the Hessian changed to this. So if I combine P with H hat, call it G hat, it's just G hat transpose as G hat. Now what's G hat? G hat is H hat times P. So this is H hat, and this P is U and D inverse. And multiply U on H hat is to subtract mu A transpose from each of the H1 to Hn here. Remember, mu A is just the mean of them. So this just to center H1 to Hn. And then multiply by 1 over the diagonals of sigma A, the variance is just to scale each of Hj by the variance. So the result here is after this multiplication by P, the Gi here are actually normalized to have 0 mean and unit variance. Okay. All right. So what's good is that. So I mean, so this is kind of equivalent to a Hessian with 0 mean and variance. Okay. So what good does that do? Well, first of all, so the first column E, if G the columns are centered, then first column E is orthogonal to G. Okay, so each transpose G is equal to 0. And we can prove that if that orthogonality improves the condition number. So it's always less than or equal to that. And second, when we scale that by the variance, we basically normalize each column of the G matrix there to have norm squared in. Okay, and in other words, all the columns of G hat have the same norm squared in. Now, if you scale all the columns of a matrix to have same norm, then by a theorem of Fundus-Lewis, that the condition number of the matrix is within the small factor of the optimal diagonal scaling. So it's within this factor of minimum of the condition number of the diagonal scaling on the H hat. So in other words, if I have a H hat U that has variance, say have a large variance between sigma A here is a vector, remember that. So among different entries, I have a large variance. Then H hat U will be badly scaled, so it will be ill conditioned. But G hat, in that case, the optimal scaling, this one, the minimum of this, would be much smaller than the condition number of H hat. And our scaling of G hat will be within the small factor of the optimal scaling. So in that case, it will substantially improve the condition number. Okay, so this is how we improve the condition number. Now, another benefit of this transformation is that it could also allow us to scale the Hessian to have about the same norm. So the norm is important because if you remember that we need the learning rate to be less than 2 over the norm. Now, remember this Hessian here is just about one layer. So at different layers, if different layers the Hessian have different norms, then we'll have to use the a learning rate that's conformed to the the one with the largest norm. So we have to use a smaller learning rate for all layers, and that's undesirable. So it turns out we can use a result from the random matrix theory to estimate the norm and then to scale that. So here's a result from the random matrix theory. So if I have an n by n matrix, each entry is a IID random variables with zero mean and unit variance, then the expected value of the norm of G is bounded by the maximum of square root m and square root n. Okay. So for our problem, the G hat, you have first column is 1, but the remaining G are not, the G are normalized to have zero mean and unit variance. So that G, we can apply this bound. Now G hat, the first column and the remaining column are orthogonal. So the norm of G hat can also be expressed in terms of norm of G and the first column, the norm of the first column. And they came out to have the same norm, same bound like this one here. So it turns out if I use Q to be this number and scale the norm of G hat by Q, then the expected norm of G hat is bounded by C times square root n. Okay. Now n is the mini batch size. M is the number of neurons in the hidden variable in the layer, okay, for the hidden variable. So by doing this scaling, this norm becomes independent of the layer. It doesn't depend on M anymore. Instead, just depends on N, which is the mini batch size, which is the same throughout. So we are able to make the norm basically similar. All right, so here's just a summary of the preconditioning method that we have talk about. So basically, in the neural network training, we just train as usual computer gradients of weight and bias, and then you take the mini batch input to the layer A there. We compute the mean and variance of that, and then we actually, for practical purpose, we use some moving average of the mean and variance. That's found to accelerate a little bit better. And then for the variance, we add a small epsilon to prevent division by 0. And then Q the scaling for the norm scaling. And then you just modify the gradient and gradient with respect to weight and bias as this. And then trained as usual with the new, with updated gradient. So that's the overall algorithms. Okay, so now let me.
Before you continue, there's a question about the last theorem, I think. It says, does the theorem only hold for initialization since after training, the weights become dependent on one another? Randomly.
Well, weight, okay, so weight becomes, no, the GI, the G here, after normalizations, I mean, technically it may or may not be independent, but it can be modeled as independent. Because GI after normalization, I mean, you know, it's possible that some of, let's say some of the weight all turn out to be the same. They become dependent. It's possible, but it's highly unlikely.
Yeah. Okay. So formally, though, I guess the theorem only holds in the first initial round.
Technically, yes. So I mean, so this holds when that's independent. Yes. So, but
all right.
But after training, I mean, there could be an extreme situation to become dependent, but typically we don't expect it to be the case. Yes, so I mean, it's correct to say that.
Yep.
Okay, so let me talk about convolutional networks. So convolutional network usually is for image data set. So where the input is a color image of 3 channels of 2D images. So what's special about convolutional networks? Usually we contain something called convolution layer. So convolution layer has a 3D tensor input and a 3D tensor output. And the input has a R by S, you may consider as image, so R and S are spatial dimension with C channels. And the output usually you could have used the same dimension, but it could be smaller or larger, but that doesn't have to be. But here, for convenience, we just consider they have the same output dimension, something called same convolutions. And then the output channels usually may not be the same as the input channels. And the output is related to input through a weight kernel. And weight kernel is a 4-dimensional tensor with a k by k in spatial dimensions, and then with C channels corresponding to input channels and C prime corresponding to the output channel. And this output is determined from the input through this equation here. So for each fixed output channel D, you take the for each input channel I, you take the convolution, the 2D convolution of the input H with the weight in the first two dimensions, also referred to as spatial dimensions, and then sum them over all the C channels, and then plus the bias for the D. This convolution is defined here, so this is what we call same convolutions, where the output is the same as input. This is slightly different from the definition of math. In math, the convolution usually we have the indices reversed, but in neural network, usually it's just the indice goes in the same directions. Okay, so let me and then also with zero pattern. So let me show you an animation that I found on the internet for the convolutions. So you have this is called feature map. Let's just look at 2D features here. And then we pad it with zeros along the borders. And then say for a 3x3 kernel, so you just slide the kernels through the feature map. And because with that zero padding, we can get the same convolution output at the same dimension. Okay. So going back to here. All right. So of course, CNN also involves things like the pooling, etc. But those are not really very too special, very routine. So let's look at applying BN to batch normalization to CNNs. So the direct application would suggest using something like this. You take the activation, subtract it by mean, over variance, and then rescale and recentering. The mean and variance will be, well, the mini batch mean, the mean and variance taken over the mini batch. But this apparently doesn't work. So actually for CNN, we use mean and variance over the mini batch and the spatial dimensions. Okay, so it's over the three dimensions. The question is why? It's not well understood. So that's another thing that the BNP or preconditioning approach has an advantage. With preconditioning, we can actually derive this process for CNNs, and there we'll see that the mean and variance will naturally come to be the mean and variance over the mini batch and the spatial dimension. Okay, so let's talk about preconditioning for convolutional network. So for one convolution layer. So here the key, basically everything's the same as before. The key is to write out the Hessian in terms of its dependence on the mini batch. So in that case, we need to write out the output as a function of the weight, in this case, weight tensor. So let's just look at the output for the convolution part. So first, write the vector form of the convolution of the two input and the weight, and we can write it as a linear function of the weight matrix here in the put in the vector form as a matrix times that. Okay, so here's an example to show what that is. So if I weight here, let's say 3x3 weight kernel, we're just looking at in the spatial convolution. So that would be this dimension 9 vectors. And then HP is this matrix here. What is HP? Well, each column of HP is just basically which it's how it's contributed to the output of the convolution as multiplied by one of the Wij. So for example, the first column here is the entries. They are consist of entries that are multiplied by W11 that contribute to the convolution output. So what are those entries? Well, if you look at that the picture that I showed you earlier, so you look at one by one, what entries in that padded matrix that are multiplied by W11? Well, it will be for W11, it will be top left 4x3 submatrix in the top left corner. So counting the two zero order rows, so it's just the top 3 rows and the top 2 columns, leftmost 2 columns of that feature matrix. And then for the second column, well, is whatever that's multiplied by W21. So W21 just one entry below W11. So it just shift the matrix down 1 row. So you'll be on that padded matrix, you'll be the entries from row 2 to row 1 to row 4, excluding the row 0. And then column will be from column 0 to column 2, the first 3 columns, and so on. Okay. So basically, each column here is consists of the elements in that R by S submatrix or 4x3 submatrix of that zero-bodied matrix that's multiplied by one of the Wij. That's important for what I will try to explain later on how the mean and variance are computed. Okay. So from that, actually, now I'm going to really rush through this slide here. You can write out to basically translate the previous equation, this equation H hat W hat, to a mini batch and over all this C input channels. So when I do that, then I put all C input channels of weight together, stack them into a long column vectors, and output for n mini batch. So there are n outputs, and for each of them, you stack the output into a column vectors. So there will be also a long vectors there, but they have this simple linear relation, H hat times W hat. But now H hat is this matrix, very similar to what we had before, 1, 1, 1 on the first column and H. But now H is this block matrix, okay? Once you have that, then everything is derived in the same way. So I'm going to skip all these details here. But so for the convolutional network, the same, we have a mean loss function, and then the Hessian is given by this, okay? So again, you have H hat here. The H hat is just the matrix H hat that I derived earlier here, that involved in that input from the weight to the output. And S here is again a diagonal matrix, actually a block diagonal matrix with Hessian in the middle. Again, that depends on the second order derivative of the loss functions, but H hat here is the one that describes how it depends on mini batch. Okay. All right. So again, we want to improve the condition number of that by try to precondition the H hat matrix, which is this one here. And it's done the same way. We use a precondition matrix P is UD, basically everything the same. So U is like there. Now the mu, what's different is what's the mu, what's the sigma, okay? So the mu should be the mu here is a vector, okay? So it should be the row sum of this H matrix, or the row sum that give you this, and divided by 1/NIS. So it's really the mean of all the row vectors of H matrix. And sigma A squared is the variance of all the rows there, okay? That's the same thing as we have before. Now with that, with that mu A and sigma A, then we have all the same property like before. You know, after transformation, you got the G hat, and G hat will be normalize, and then that improve the condition number. Okay. Now, what's really different is what is this mu a? Okay. So this mu a here is the basically the mean of these rows. So let's just look at, say, the first entry of this mu a. So the first entry will be the mean of the first column entries here. Okay. So what's the first column entries there? Well, there are n blocks corresponding to n mini batch inputs. So that's the sum of that. When you divide it by n is the mean over the mini batch. Now for each block, you look at its row. So let me go back to that matrix that I talked about earlier. So if you look at one row of this matrix, so as I said earlier, there are entries of an R by S matrix, submatrix of the zero bounded matrix there that's multiplied by one of those Wij. Okay, so the sum of that and sum over all n mini batch is the mean of elements of the n R by S submatrices of the zero pattern matrix. So that's the mean across the mini batch examples and also across the spatial dimensions. Now, this one here, each entry of mu a will be different for different Wijs. We believe that should be the precisely, or at least theoretically, that should be the way to do it. But that's computationally expensive. So they can, for small kernels, they can be they are approximately just mean variance of this over the mini batch and the spatial dimension. And that's the one that's used in BN. Okay. So that through this derivation, it also shows us what kind of the normalization, why we should use the normalization involving mean variance in the spatial dimensions. Okay. Is there any question at this point before I move on to talk about experiments? All right, I'm going to show you some. You have something?
No, I was just going to say not right now. It doesn't look like it. But okay. If anyone has any questions, please go ahead and put them in the Q&A tool for after the talk is over. Okay. So I want to show you some experimental result. So so I'm going to use the standard data set CIFAR 10 and CIFAR 100. Those are color images. CIFAR 10 has 10 classes, CIFAR 100 has 100 classes. Okay. So first I want to show you the fully connected network with CIFAR 10. So here we have a very simple network that's used in the original BN paper test. So it's 3 hidden layers of size 100 each and an upper layer of size 10. So what I present here, this is for the paper. So I have several other methods in comparison there. So for us, I'm going to just look at the BN and the vanilla network that's with no normalizations, and the BNP. So the dashed line here shows the training loss, how training loss converges, so it decreases. So you can see the green line here is actually the blue line here. Blue line is the vanilla network with no normalizations. And then the red line is BN. So for this test with small mini batch size 6, we're using for this test we're showing the one with mini batch 6. The BN actually is doing worse than the vanilla network. And the black line is the BNP. So you can see that we do show significant acceleration for training. Now the solid line is the we plot testing accuracy. So the higher the better. So again here, the blue lines, the vanilla network, and the red line BN, they show about the similar performance. So BN at least does not seem to help, but it's doing better than training. And the black line is the
BNP. So at least we show much faster convergence and slightly better at N. The next picture here is for a CNN example. So here we use a 5-layer CNN. It's again, this is one of the example network used in TensorFlow. So it has the three, a very simple network. You have 3 convolution layers and then with 2 fully connected layers. So again, the dashed line here are training and solid line are testing accuracy. So for this one, we tested on, again, a small mini batch size, in this case for CNS2. You see that the BN, the red line, is underperforming the vanilla network quite substantially, but our BNP outperform both of them in both training and in testing as well. Okay, so that's CNN. Here's also one example of the online learning. So there is the mini batch size is 1. So in that case, BN simply doesn't work. So here we compare with the vanilla network. So I put the fully connected network and the 5-layer CNN both in the same figure here. So the blue line is the vanilla network, and then the black line is the BNP for the fully connected. And then you can see here that the BNP outperform in training, and then in testing also initially also quite perform substantially, although eventually they're about the same, even slightly below, probably due to some overfitting there. And the other 2 lines are for CNN. So here you have the light blue, I think light blue line is the vanilla network, and the purple line is the BNP. So in training, it looks like about the same, but in testing, the BNP is doing quite a bit better. Finally, I want to show you 2 results on the ResNet, which is a very deep network. So here is a ResNet 110, so 110 layers ResNet with 54 residual blocks. So again, dashed lines training in the solid lines testing. So I'm primarily going to look at the testing here. So the blue line here is the vanilla network. For this ResNet, the best setting involved, there are several things involved. So we follow the original setting of the ResNet. So there's a learning rate decay at 80th epochs and then 120th epochs. So the blue line is the plain network, and the red line is the BN network. You can see there. So there's a very big jump at the learning rate decay for the BN network at 80th epochs. The black line is BNP alone. So BNP alone, initially you can see here, we're doing better than BN. So we have very nice initial accelerations, but it does not perform as well as BN at the learning rate decay. So that's a peculiar property associated with ResNet peers. So at the learning rate decay, there's a big jump in the accuracy. So we believe that's probably associated with some of the scale invariant properties of the BN, which we don't have. But one way to address that is to consider BNP and group norm. So we add group norm to BNP. That can be easily implemented, but also have the scale invariant properties. With that, then the BNP plus group norm return the result is very similar, basically comparable to BN. Here's another result of the ResNet, so it's called Preactivation ResNet. Again, we're using 110 layers ResNet. And now this is tested over CIFAR 100. So the black line is the BNP alone. Initially, it's performing better than BN. The red line is BN, and but it does not perform as well as BN at the learning rate decay. But initially, it was converging faster. The green line is BNP plus group norm. So that green line performs better initially, the best, accelerate significantly, and the final accuracy is also comparable to BN. So and also it shows much more smoother convergence, less oscillatory. Okay, so those are experiments. So let me just quickly with some concluding remarks. So we have derived a preconditioning framework that can be applied to different network architectures. The method outperforms BN for small mid-batch size. And it also provides some partial theoretical justifications for BN in terms of how it improved the Hessian condition numbers, and also how BN's mean and variance normalization is done for CNNs. Currently, we're working on applying this to RNN, the current neural networks. Okay, thank you very much for your attention. I will stop here and see if you have any questions.
Great, thanks a lot for a great talk. I'll open the floor now. If anyone has any questions, please put them in the Q&A, or if you have the ability, go ahead and unmute yourselves and ask away.